Hello, Physics 1. Welcome to part 1 of Wednesday's lecture, week 16. When this lecture is over, you just have 3 more to go. Exciting, exciting. All right, so last time we were talking about angular momentum, and I introduced a directionless expression for the formula. So we talked about it, that the translational angular momentum with respect to something is equal to the magnitude of position times the magnitude of momentum times the sine of the angle between them. But we have not yet talked about how to determine direction from this. Now, there's 2 ways to do this. We're going to start off with one where we get to introduce something called the right-hand rule. All right, so we need direction in so many ways these days. All right, the direction, so in our previous setup, looking at the angular momentum as the Earth or Mars is going around the sun, we saw that it was traveling in the xy plane, and the direction of the translational angular momentum for this particular case will be in Z. That's right. This is the reason why we have been working on thinking in 3 dimensions all semester long. So we can start to do things that have components in all 3 coordinate planes like angular momentum, and we can do them to their fullest. All right, so for some of you, I used to say the easiest way to do this is the right-hand rule, but I have found that it just really depends on the student. So one of the potentially easier ways is the right-hand rule. So we can use the right-hand rule. And this is something that we are going to see again in Physics 2. So I will abbreviate RHR. And so for this, you need your right hand, not your left hand. The left hand will give you the wrong answer. You need your right hand. So the right hand rule for circular motion. So in the case of the Earth going around the sun, I said it goes counterclockwise. So you take your right hand like so, and you curl your fingers in the direction of motion. So see, I'm curling my fingers. Now, the important digit that you want to pay attention to is your thumb. So here's my thumb. I know I've not painted my nails this week. It's just, what can I say? We're all tired. All right, so, and we see that this is pointing up in positive Z. So we have X, we have Y, this is positive Z. By the way, this would be true if we were working in the YZ plane, then angular momentum would be in X. If we're in XZ, angular momentum would be in Y. So in this case, we've got counterclockwise motion. Motion in the XY plane results in plus Z. So our unit vector for translational angular momentum is out of the page, which is how we often describe. So into the page, you'll see into the page in just a second. So out of the page, that's often how we describe going in the positive, often Z direction, although like I said, you need to be careful that you're reading the correct planes for where this particular interaction is taking place. Okay, so we've seen counterclockwise. let's look at clockwise. And no, if you were to ever take this in my classroom, a quiz on this, I never hide clocks. I will always let you see what direction a clock goes. All right, so clockwise. And once again, let's just stay in X and Y. So that means we're going to be finding the direction of angular momentum in Z. So we're going to curl our fingers, and we see, I'll do an angle, your thumb is pointing into the page. So you may feel a little bit silly, but I would actually recommend for both of these, taking your hand up to your computer screen and practicing this. For some of you, it's going to be supernatural. I always have a student or two that just needs to go through a few times. It's okay. It is no marker of intelligence or understanding. It has to do with spatial reasoning, which has nothing to do with intelligence or understanding. It's just how it's, anyways, I'm going off on a developmental psychology tangent. I will stop, but just recognize this is just one of those things that some students seem to get very quickly. Some students seem to take a little bit more time with it, and I have found that it is never an indicator of ability. All right, so in this case, we can see clockwise that the thumb is going into the page. So we would have negative Z. So clockwise in Y, in XY, angular momentum, minus Z. And so the direction of translational angular momentum is into the page. So out of the page, positive Z, into the page, negative Z. That's the standard convention. Always be careful how you're setting up your coordinate system because you are allowed to set stuff up strangely if you want to. You could decide that this is your minus axis and this direction is positive. I mean, I don't really recommend doing that at this level. Where you start to see some strange axis choices is sort of in more advanced setups. And as I've said before, one of the computer simulation models I did, I had a bit of an unusual coordinate plane setup, and it had to do with my perception of the experiment so that I didn't have to enter a negative sign for something that I was thinking in a positive direction, even though it was going to the left. Normal thing to do, you pick your coordinate planes. In Physics 1, pick reasonable ones. Once you get comfortable with them, you can be a little bit more creative. All right, so now we know how to find the direction using the magnitude calculation for angular momentum. It's that magnitude of r, magnitude of momentum, times sine theta of the angle between them, and you determine the direction of circular motion with your hand, which gives you where angular momentum is going to be, generally in Z. Now, we need to get it into a vector. Because, of course we do. So, in our Mars example, we had counterclockwise motion. So our direction of translational angular momentum was in positive Z. So the translational angular momentum with respect to the sun, any vector can be broken down into the magnitude vector, which we've already calculated, and its unit vector, which we found using the right-hand rule. So I'll make a note, calculated, and right-hand rule. And so this is equal to 3.42, oh my goodness, let me try this again. This is equal to 3.42 times 10 to the 39 kilogram meters squared per second times 0, 0, and it's positive 1. And so this is equal to 0, 3.42 times 10 to the 39 kilogram meters squared per second. And there you go. Translational angular momentum as a vector. Okay. So, I have told you that planet motion is nearly circular. We can very safely make that estimation and get pretty darn accurate. But what if, and we've seen that translational angular momentum stayed the same. Let's see about a highly elliptical orbit. Specifically Halley's Comet. It's one of the most famous comets, goes around every 73.3 years. So fun or interesting story, maybe not fun, about Halley's Comet. So Mark Twain was born on a year that Halley's Comet came around, and he predicted his own death. He said, I came in with the comet, I'm going to go out with the comet. And he passed away the year that Halley's Comet came back. So he was correct. And there have been a number of people who have accurately predicted their own death. He's one of them. And he did it along with Halley's Comet. I'm not saying anything about whether or not that means anything more than maybe he was just making a guess. All right, so in this case, our P, so displacement, momentum, and theta are not constant. They are changing. They are changing. Unlike a circular orbit. Of course, if you're really into looking at planetary orbits and comet orbits, I'll give a shout out. This class was around last fall. It'll come around again a year from fall. I do teach an Introduction to Astronomy course. It is a gen ed science class, but I have found that my physics students got a lot of enjoyment out of it because the mathematics are brought down to a basic level, and you just get to learn about the universe and space and stars and their life cycles, and you get to do really straightforward calculations and get your mind blown on a regular basis and talk about what would happen if you were to cross the event horizon into a black hole. Let's just say it doesn't end well for you if you do that. So if you have extra time in your schedule next time it comes around, you are able to take it without the lab component, and I have fun teaching the class. I think it's an enjoyable experience, and I love having advanced science students in the class because they just really bring something special. Okay, so there's my sales pitch over. Is the angular momentum of a comet relative to the sun constant? All right, so Halley's Comet, I've said these things in words, now let me put them in writing. Orbits the sun with a period of 73.3 years. By the way, it's next visible in 2061. So last time it was visible, I believe it either came just before I was born or just after I was born. So I've never seen Halley's Comet. So maybe I'll get to see it next time around, God willing. But you can go ahead and mark your calendars for 2061. All right, so we have the comet the orbit does look more like this, like what you see. There it is, going around the sun. Okay, so let me give you some drawings. Here's the sun. Comet ship. Blue. We'll stick with blue. Here is the comet at position A. Yeah. So we have R1. And then we're going to have the comet going around to position B. I'll write that in a second. So that's R2. We have momentum 1, momentum 2. So I'll draw a little. And we've got, let's see, some angle theta right there. And so we've got A and B. Okay. Not the best drawing, but you get the gist. Jeez. All right, so R1 vector is equal to (8.77 times 10 to the 10 meters). V1 is equal to 5.46 times 10 to the 4 meters per second. R2, and of course, theta 1 is 90. We already know how to do that. R2 is equal to 1.19 times 10 to the 12 meters. V2 is equal to 1.32 times 10 to the 4 meters per second, and theta is equal to 17.81 degrees. Okay. Oh, one more thing so that I can just, the mass of the comet is equal to 2.2 times 10 to the 14 kilograms. All right. So we want to look for the translational angular momentum at A and B. So we want the translational angular momentum here and the translational angular momentum there. We want to see if there's a change. So we need to calculate it in two places. We've got clearly have some really different things going on in every place. The only thing that's staying the same is the mass. Okay. So let's look at the direction. And we're going to use the right-hand rule. I'm going to bring my picture back. Okay, so it's going in that direction. See, we go from here to here. Thumb going down. That means it's a negative Z. All right, so negative Z. So arrow there just to remind you. Negative Z. Okay, so at A, translational angular momentum with respect to the sun is equal to 8.77 times 10 to the 10 meters times 2.2 times 10 to the 14 kilograms. I'm running out of room, times 5.46 times 10 to the 4 meters per second times sine of 90 degrees. This is equal to 1.1 times 10 to the 30 kilogram meters squared per second. Okay, interesting. And so we said it's going in negative Z. Let's put that into a vector. L translational with respect to the sun, so there we go, is equal to 0, 0, minus 1.1 times 10 to the 30 kilogram meters per second, or meters squared per second. Okay. Now let's look at B. All right, so translational angular momentum with respect to the sun at B, we have 1.19 times 10 to the 12 meters times 2.2 times 10 to the 14 kilograms times 1.32 times 10 to the 4 meters per second, all multiplied by a sine of 17.81 degrees. Make sure your calculator's in degrees, not radians. And so this is equal to 1.1 times 10 to the 30 kilogram meters squared per second. Let's put that into a vector, the vector of translational angular momentum. Once again, it's a negative z. And this is equal to 0, 0, minus 1.1 times 10 to the 30 kilogram meters squared per second. But, Dr. Grace, you might be saying, that's the same number. And to which I would say, yes, it is. Angular momentum, translational angular momentum doesn't change, even if you have a highly elliptical orbit like a comet. And this is really something that's worth working through the calculations yourself to do, because I could have told you that, but you shouldn't have taken my word for it. You should have done this. So once again, we see translational angular momentum is the same. It's the same in the magnitude. It's the same as a vector. Pretty cool. So I'll write that out. Even with a highly elliptical translational angular momentum is constant throughout orbit. There was nothing giving it a twist. So this indicates that angular momentum is a conserved quantity. So I told you this before, but you're good students, you don't take my word for it. You want things proved. Well, here you go. Okay, so something to note though. You may have, and maybe you've already picked up on this. When we calculate translational angular momentum, we only know position and momentum at that instant. We actually don't know where it's going next. We just looked at A, we looked at B. We took the information from A, we looked at the information from B. We knew that it was, in these cases we did actually have some information, but you could only be given a position vector, a momentum vector, and the angle between them. So, for example, let's say you've got something, you've got this point and something has momentum like this. So maybe it's going to go like this. Maybe it's going to be circular. Maybe it's going to be elliptical. I have drawn something that I can't fit on. Zoom out. Maybe it's going to go in a straight line. Do we know? Nope. Not if all the information we have is that point. We don't know. We only know that in that moment, it has this distance, it has that direction of momentum. We don't know where it's going next. But we can still calculate the angular momentum. There you can see more of how I work. All right, so what we can see from this is we will later see why it might be useful and meaningful to attribute angular momentum to straight line displacement. So we could have been calculating angular momentum as early as chapter 1, although we needed to really build in a nice understanding of vectors first. Okay, so moving on, there is another way to calculate angular momentum. And for this, I need to introduce you to our final vector operation for Physics 1, the vector cross product. There's two ways to multiply vectors. One produces a scalar, you've already seen it, it's the dot product, and the other produces a vector. This is the cross product. All right, so let's see. We have vector A, vector B. They have some theta between them. And this is A cross B. So one visual depiction of what we're building towards doing. All right, so we will need the cross product for angular momentum calculations. Oh, and for those of you that have taken linear algebra or calculus 3, you are welcome to go ahead and skip this. I don't know how many minutes it's going to be. By the way, even though this topic is covered in those classes, it is a basic multiplication operation. It's just done in 3 dimensions. So to do it, you only need algebra skills that you would learn in Algebra 2. Okay, so I think you still call it Algebra 2 in high schools. We have already seen we've already done one version of a cross product. So you're already halfway there. L is equal to R times the magnitude of R times the magnitude of momentum times sine theta of the angle between them is just the magnitude of R cross P. So you see that typical multiplication sign. That is the cross product operator. I'm also going to state at all. Very different operations. Very, 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 very different operations. All right, so for what we know, the direction is given by the right-hand rule. So in this case, you can still get that vector conversion by just determining the motion, and you've got it. By the way, you can do this, you can actually determine the direction of motion without even knowing the circle. You can do it with just the two vectors, which is what we're going to do next. By the way, just something to note, theta is always less than or equal to 180 degrees. All right, so I'm going to get a fresh sheet of paper because I want to draw big drawings for the right-hand rule so that you can use them. All right, so when you use the right-hand rule, you want to draw the vectors r and p so the tails are in the same location. You don't want to rotate them, but you can kind of shift them around until they're tail to tail, whatever that looks like. Okay, so let's do R in orange, P in green, theta. All right, so you want to take your right hand. This is my right hand. By the way, your left hand makes an L. I'm sure you've seen that before. I would be lying if I didn't say I sometimes still need to be reminded of that. You want to line your right hand, the fingers up, with the R vector, which comes first in our cross product. So remember, we're doing R cross P. So whichever one is first is the one that you line up. So we're lining up with R. There's R, there's my hand. We want to curl towards P. And you want to do whatever comes most naturally. You don't want to contort your hand in any way whatsoever. So it's most natural for my hand to do this. Therefore, this is in positive Z. Okay, let's look at the other setup. Let's say you have R in this direction and P in this direction. Some theta between them. Okay, so let's say I line it up like this. Ow, ow, ow. Okay, that's not going to work. Flip your hand. Curl towards P. Your thumb is going into the page. Negative Z. All right, I'm going to do both again. So line it up. So if I was to line it up like this, that's not natural. Flip your hand. Now you can naturally curve towards P, seeing your thumb in positive Z. Try it over here. Not natural. Flip your hand, line it up with R, curl towards P in a natural way. That is how you determine the direction using the right-hand rule with just two vectors. So if you know the whole circular motion, you can curl that way. That's one way. If you just have the vectors R and P, that is enough to determine direction. Okay, and let me write this out in words for those of you that like sentence. So point fingers of right hand in direction of R, fold through theta, theta toward P. May need to flip hand. And then stick your thumb out. That's the direction. You know, I mean, I told you I'd give you some direction in this life. Some of you, I'm sure, are groaning, and some of you, maybe one or two of you, are laughing along with me. Those of you that are laughing, I appreciate you. I appreciate those of you who groan too. All right, so the perpendicular distance are perpendicular. All right, so Say we have a point here. Here is R. Here is P. You want to put them tail to tail. If you draw a line, let's see, what have I not used? All the way up to here, so that it is perpendicular with the momentum. This is our perpendicular. Okay. So this is the component of R that is perpendicular to P. So through point that the angular momentum is to be calculated. All right. And I have let's see, I'm gonna try to keep this all in one area. So R perpendicular is equal to R sine theta. It's related to impact parameter, which is something we talked about in our chapter on collision. And it gives the distance of the tail of R to the line of P. So we don't do too much with it, but it is an important thing to know. All right, so moving on. I've talked about cross products. We have not done a cross product. Okay, I want to make sure that I don't have to stop my cross product explanation because I've run out of time. So I'm going to stop this lecture right here, and we're going to pick up immediately with doing a cross product. And yes, I always take my time with the cross product operation. It's something that if you haven't seen it before, I want to make sure that you're understanding every step. But it is not an overly challenging operation to do. It's just new if you haven't seen it before. All right, see you next time.